Hey guys, Mr. Backwork here. In this video, we're going to look at trapezoidal approximations. Now, back when we first learned about approximating area underneath a curve, we used rectangles to help us find that area because rectangles are easy to find the area of. But depending on what type of rectangles we used and depending on what our graph looked like, our approximation could have been an over approximation or an under approximation. So if we look specifically at this parabola, we're looking between 0 and 3. If we would have done left rectangles there, that would have been an underestimation. But if we would have done right rectangles, that would have been an overestimation. So instead, we generally used the middle rectangle approximation because that gave us a little bit of overlap, but it also gave us a little bit of under approximation as well. So we said that that kind of averaged out. But there is another way or another shape that we could use to approximate the area underneath a curve. And like the title of this video implies, it's about using trapezoids. So here we have a graph with quite a few curves in it. And we can see from these trapezoids that as our graph is curving, then the slanted side of our trapezoid generally follows the curve of our graph pretty well. Up until the very end here, that was kind of a steep increase, so that gave us quite a bit of overestimation there. But generally, these trapezoids end up being pretty good approximations for the area underneath that curve. So there's this thing called the trapezoidal rule. So if we're trying to approximate an integral of some function from a to b, then the formula we're going to use says t equals h over 2 times a whole bunch of y values. Now notice the first y value and the last y value don't have any multipliers in front of them, but all of the middle y values have a 2 multiplier in front of them. And we'll see where all of those y values are coming from as we go through our example in a couple of slides. And we're doing this over our a to b interval where that interval has been partitioned into n subintervals of equal length h, where we take the upper limit minus the lower limit and divide it by the number of trapezoids that we're going to be making. Now, equivalently, if we have gone through and done the work to find our left rectangular approximation and our right rectangular approximation, then the trapezoid rule actually ends up being the average of that left and right rectangular approximation values. And this is handy because we have a rectangular approximation program in our calculator. So if we're doing this trapezoidal rule stuff, we can use our program to help us find our answer or check our answer. And we'll see that as we go through our example on the next page as well. So in this example, we're going to be looking at using that trapezoidal rule. So we're going to use our trapezoidal rule with an n value of 4 to approximate the integral of x squared dx from 1 to 2. And we're actually going to do a lot with this one example. We're first going to do it the long way by using the trapezoidal rule formula. And then we're going to check our answer using our calculator and our RAM program. So we're going to find the left rectangular approximation and the right rectangular approximation, and then we'll average those values. And then we'll do the actual integral to figure out how close our approximations were to the true area underneath the curve. So like I said, we're going to do things the long way first. So the first thing we need to figure out is our h value, which really kind of ends up being the height of our trapezoids. So we said to calculate the h value, we take the upper limit from our integral minus the lower limit from our integral, and then divide that by the number of trapezoids we're going to be forming. Well, on top, 2 minus 1 is 1, and on bottom we get 4, so we get an h value of 1/4. Now, I said that we were going to need to calculate some y values, and here's where this h value is going to come in handy. I'm actually going to make an x and a y table. Now, we know that we're starting at an x value of 1, and we're making quarter-sized steps until we get to the x value of 2. So our first x value is 1, and then if I go 1/4 from that, well, I would have to get common denominators. That's going to end up being 5/4. And then if I take another 1/4 step, that's going to be 6/4. I'm not going to worry about reducing that down. If we take another quarter step, that's going to be 7/4. And then another quarter step would be 8/4, which is 2. And that's our last x value that we want. Now what I'm going to have to do with these is take each of these x values and plug them into my x squared formula. Well, if we square 1, we get an answer of 1. If we square 5/4, to square a fraction, you square the top and the bottom. So that's going to be 25/16. If we square 6/4, we're going to get 36/16. Squaring 7/4, we're going to get 49/16. And squaring 2, we're going to get 4. Now, using our actual trapezoidal rule formula, this says t equals, we want to take that h value, that 1/4 that we got, and we're going to divide that by 2. And then what we're going to do is a bunch of adding with these y values. So we take the first y value, which was just 1, but then we add on. Now, with these middle y values, we need to multiply all of them by 2. So I'm going to take 2 times the 25/16, and then I'm going to take 2 times the 36/16, and then I'm going to take 2 times the 49/16, but then with our last y value, that 4, we just want to keep it the same. We don't multiply it by 2. Now in front, 1/4 divided by 2 just ends up turning into 1/8, and then we've got all of this addition happening inside of our parentheses. If we were to go through and do all of that adding and multiplying, we'd end up getting 75/32. But if we turn that into a decimal, we get 2.34375 as our trapezoidal approximation. Okay, so that's the first step. I said that we were going to do it the long way to figure out how we can approximate the area underneath the curve using our trapezoids. But now we're going to use our RAM formula on our calculator. We're going to figure out the left rectangular approximation, the right rectangular approximation, and then just average those values. And hopefully we get the exact same thing that we just got. So in my calculator, to do my RAM formula, the first thing I need to do is go into y equals and hit x squared, since that's the function that we're integrating. Then I'm going to quit out of there and hit my program button. I want my RAM program. Number of intervals, we said that we had an n value of 4. Our left endpoint, or our lower limit of the integration, was 1. The right endpoint, or the upper limit, was 2. So here's our 3 different rectangular approximations. To do our trapezoidal rule, we said that we were going to take our left approximation, which is 1.96875. We were going to add that to our right approximation, 2.71875. I'm going to get an answer there, and then I'm going to split that answer in half. And we should notice that this calculator answer matches up with what we got when we did it the long way. Now, we also said that we were going to do the true definite integral to figure out what our answer should be so that we could see how close we got to that answer. So doing this definite integral, the very first thing I want to do is the antiderivative of this x squared. And since that's x being raised to some power, what I want to do is take 1 over that power that I was given, but add 1 to that. So that's going to be 1/3. And then I take my x and I add 1 to the power, so that becomes x cubed. Now we can turn this into just x cubed over 3. And then what I want to do is evaluate that at the upper limit of 2, at the lower limit of 1, and then subtract those answers. So if I plug in 2, 2 cubed is 8 over 3, so we get 8/3. Then if I plug in 1, 1 cubed is 1 over 3, I get 1/3. If I subtract those answers, I get 7/3, which as a decimal ends up being 2.3 repeating. So as we can see, our trapezoidal approximation got us pretty close to the true answer using only 4 subintervals. Now, if we're trying to get more accurate with our answers, we would want to break this up into more and more subintervals, but 4 subintervals, again, got us pretty close. Now, in this example, we're going to be looking at averaging some temperatures. So an observer measures the outside temperature every hour from noon until midnight, and they record the temperature data in the following table. So we can see all of the times here, and we can see the temperature readings. We want to figure out the average temperature for this 12-hour period. Now, we're finding an average value, so our average value formula is 1 over the upper limit minus the lower limit, and then we multiply that by our integral of some function f of x dx from a to b. Now, if we think about this noon as being our time of 0 and running along those times until midnight, that's at our time of 12, then really we're looking at an a value of 0 and a b value of 12. So if I start setting up this average value formula, then I'm doing 1 over 12 minus 0. of some integral. Now, we don't really know what the function is for these temperatures, but we can use our trapezoidal rule to approximate the integral. So what we're going to do is take our trapezoidal rule, where we do that h over 2 times all those different y values. Now here we're measuring the temperature hourly, so that really makes our h value 1. So then in the front, when I start doing my trapezoidal rule, when I do h over 2, that's just going to be 1/2. And then I have to multiply all of these different y values together. But remember, the first and the last y values don't get any multipliers on them, but all of those middle y values will get a 2 multiplier on them. Now, if we look at simplifying this down, first looking at this fraction, 1 over 12 minus 0, that's 1/12, and then 1/12 times 1/2 is 1/24. Now, all of this multiplying and adding inside of our parentheses gives us 1,564. And then if I take that and multiply that by that 1/24th, or divide it by 24, then I get an average value of about 65.17. Now, all of our data just gave us 1 decimal place worth of accuracy, so we can just say that our average temperature is about 65 degrees. That's going to be it for this video. Thanks for watching.